Hi, I'm Kristin Ulmer from Southwest Research Institute, and coming up next, it's time for summer school with lateral earth pressures. Thank you for tuning in to this video. Today I'll be sharing a quick lesson on lateral earth pressures as part of the Geo-Institute Summer School video series. My name is Kristin Ulmer. I am a senior research engineer at Southwest Research Institute in San Antonio, Texas. Before I get started, I have to acknowledge the many people who have helped me learn this material in the first place and prepare a lot of the material that you're going to see today, which I did teach as part of one course I taught as a PhD student. So many thanks to my professors at my undergraduate institution at Brigham Young University and my graduate professors at Virginia Tech, and also the other PhD students who went through the same teaching experience that I did and shared their tips and tricks. As a note, in order to understand fully everything that you'll see in this presentation, you'll want to know a little bit about soil classification, what's gravel, sand, silt, clay, things like that. A bit about effective and total stresses in soils, knowing the difference between those two things and how to compute them. Also, estimating vertical stress at a depth in a soil profile, a little bit about Moore's circles, and understanding soil shear strength envelopes. So we're talking about friction angle, cohesion, things like that. If you don't already know a lot about these, or at least a little bit about these things, I think you'll still get something out of this presentation. But if you get lost anywhere in the middle, you may need to go Google some of these and find some other helpful videos, maybe even some videos as part of this series. So, assuming you know how to estimate vertical effective stress, or sigma prime V, in a soil profile, how then do you estimate horizontal effective stresses, sigma prime H? And why would you even want to know that? Well, you may have seen retaining walls or other structures like this that are meant to hold soil up. You'll want to know what is the pressure acting horizontally on this wall, for example, so that you don't have a problem like this, where your wall is tilting. Well, it depends. Trying to estimate these horizontal stresses depends on a lot of things. And after this video, you'll understand the basics of computing lateral earth pressures using Rankine's method for 3 different cases: at rest, active, and passive. And I'll explain all of these concepts in just a few moments. Let's start with at rest conditions. So at rest indicates no lateral movement in the soil. So imagine you have a point in the soil profile here that you're wanting to estimate stresses for. Here's the ground surface. Here's my water table marker saying water is up here at the ground surface. And we know how to compute sigma prime V based on the unit weight of the soil above this point and the depth to this point and any pore pressures that may be there. But we want to figure out what's the horizontal pressure in this at-rest condition. The key to that is this K0 parameter right here. So at rest conditions, as I mentioned, there's no lateral movement in the soil. That's your assumption. And this could represent something like large aerial fill, where you have all vertical compression or consolidation happening equally across a large extent. This could be fill placed along a non-moving wall, like a basement wall. So it's not moving in, it's not moving out, it's staying put. So that's sort of an at-rest condition. You could also consider natural soil deposits like what we're illustrating here in this figure. To estimate K0, there are a couple of popular equations. One from 1944 that's based on the friction angle, the effective friction angle, which is this V prime right here. Now recognize that this equation is for normally consolidated soils. So that's where your over-consolidation ratio is equal to 1. Now that's from another lesson as well on past pressures for soils. So this is indicating that the soil is currently under the maximum stress it has experienced in its experience in this deposited state. There's a version of this equation that's slightly modified for soils that aren't normally consolidated. And that's here from 1982, based on that same friction angle again, but now we're inserting OCR, the overconsolidated ratio, as an input. And you'll see it's OCR to the sine of phi prime for any OCR above 1. So this is the K naught for at rest conditions. So your lateral earth pressure coefficient, or K, at rest. So the horizontal stresses acting on this particular point right here would be the vertical stress multiplied by K naught, which is dependent on the phi prime, the friction angle, and potentially the OCR if you have a over-consolidated soil. So that's at rest. Your K naught for sand is typically less than K naught for clay. K naught increases with your over-consolidation ratio. The horizontal stress is sort of locked in after the vertical stress is decreased. So even though you're releasing some of that vertical stress, some of the horizontal stress just kind of stays locked in because you don't have as much relaxation horizontally when you're in these at-rest conditions and you have soil on either side. So you can see for sand and clay, here's some sort of typical condition or typical K naught values for these two types. And as I mentioned, sand is typically a little bit less than the K naught for clay. So now you understand K naught at rest. What about when the soil is not at rest? Let's talk first about active conditions. So in this case, active indicates lateral movement of an object like a wall away from the soil. So in this case here, we have the ground surface here with a nice retaining wall drawn here. And then the ground surface continues up here, back behind the wall. And the wall here is going to move away from the soil that we're showing right here. Again, we have this point in the soil profile where we know what the vertical stress is, and we want to figure out what is the horizontal stress in that soil at that point. Here we're just considering a sand with a C prime of 0, right, meaning no cohesion. And the sigma prime V would be constant. So if this wall moves away from the soil, the vertical stresses will maintain their level, and then the sigma prime H would decrease, right? You have a little bit less stress acting on this particular soil right here. So typical case for soil behind your retaining walls, you typically plan on active conditions. How do we estimate the lateral earth pressure coefficient for active conditions? This is the equation that you would use in the Rankine theory. So Ka is tangent squared of 45 degrees minus your friction angle divided by 2. Now, how do we get that value? I'll show you a little bit on the next slide how we get there using more circles. Here on the vertical axis of this plot, we have shear stress. On the horizontal, we have your vertical effective stress, or rather just your effective stress. Horizontal and vertical are both going to be represented here. Right here is our strength envelope. So it's at an angle of your friction angle phi prime. It's intersecting the vertical axis at 0. So we're having no cohesion in this case. So initially, your soil is at rest, right? So I'm highlighting that here, this blue half circle, the upper part of the Mohr circle, where the diameter of the circle is defined by your vertical stress and your horizontal stress, where horizontal stress at rest, right, is our K naught at rest times your sigma prime V. So this is representing the stress conditions at rest. As your wall moves away from the soil, you'll decrease this sigma prime H, right? So it'll move, as you can see with this arrow, this direction, right? We're moving this lower part of the circle to the left, decreasing it till we touch the strength envelope, right, which is highlighted with this red Mohr circle. At that point, we're fully mobilizing the shear strength, right? We have intersected this strength envelope. At that point, when this Mohr circle is touching the strength envelope, this horizontal stress is what we assume for active conditions using the Rankine theory. So sine phi prime, if we sort of use some trigonometry here using these different Mohr circles, we can represent sine phi prime is equal to 1/2 of sigma prime V minus sigma prime H, right? Over 1/2 of sigma prime V plus sigma prime H, right? So that could be said here, that is said here, only where we're actually touching the friction angle, the shear strength envelope. So rewrite that as sigma prime H is equal to sigma prime V times this ratio of 1 minus sine phi over 1 plus sine phi. rewrite this again. So 1 over sine phi, 1 minus sine phi over 1 plus sine phi. You can rewrite as tangent squared of 45 minus phi over 2. These are just using some trigonometric relationships. And now this is what we were looking for in the first place, right? Was our horizontal stress is equal to the vertical stress times some multiplier, right? Which in this case is that tangent squared term. So we can just replace this tangent squared term with our Ka, our active lateral earth pressure coefficient. And that's what we get. And this is the equation I showed in the previous slide. Now note this equation is written for a condition with no cohesion. There are modifications to this equation that would incorporate cohesion, but I'm not showing them in this particular presentation. And we'll talk a little bit more later about why maybe you just want to focus on this. Let's do a quick example. So here we have a retaining wall with backfill soil behind. Here's the ground surface. In this case, I'm having no water behind the wall, no water table, no pore pressures to deal with. The height of the wall is 10 feet. You have 100 PCF soil, so that's your total unit weight of the soil. The friction angle of the soil is 35 degrees. So let's first calculate our vertical stresses. So you may have seen a diagram like this, where we're plotting your vertical stresses on this horizontal axis versus depth. So as you increase your depth, you're going to increase your vertical stresses on a slope of your unit weight times your depth. Z is depth in this case. So at the bottom of that 10-foot wall, we would have 100 PSF as the pressure. So now we have our sigma prime V profile. Let's compute our sigma prime H, our horizontal stresses. We need our lateral earth pressure coefficient, our K sub A, if we're assuming active conditions, which is typical for retaining walls like this one. This is how we would compute our Ka. In this case would be 0.27. So now we're going to plot our sigma prime H. It's simply that Ka we just computed, which is constant with depth in this case, at least that's our assumption, and multiply it by our sigma prime V, which changes with depth. So now the slope of this line is Ka times your gamma times Z. So you draw this triangle right here. At the bottom of that 10-foot wall, we'd have 270 PSF is the pressure. And because we just have one single triangle of pressures acting on this wall, we know that the resultant pressure will be acting 1/3 up from the base of this triangle, and we can compute the total force acting on the wall. So the resultant lateral force P sub A acting on this wall would be the area of this triangle right here, representing our horizontal pressures. So that's 1/2 times Ka gamma T, which is the unit weight, times the height of the wall, times the height of the wall again. So 1/2 270 PSF, that's the total pressure at the bottom of the wall, times 10 feet. You'll get about 1,350 pounds per foot of wall length. It's going to be your resultant force, and it will be acting 1/3 of the total wall height up from the bottom. So in this case, 10/3. All right, so that's one quick example of using these equations to compute the horizontal force and the horizontal pressure acting on this particular wall. So we talked about at rest and active conditions. And I mentioned a third condition. This is passive conditions. So passive indicates lateral movement of an object, or like a wall, into the soil. So we talked about no movement of the soil. We talked about an object moving away from the soil. Now we're talking about an object moving into the soil. Now, when would you worry about that? One example might be this wall here moving away from the soil here. So we'd have active conditions behind the wall. But just in front of this embedded wall, you would experience some passive conditions, right? The wall is moving into the soil that's here in front of the wall. So this is a typical case for the base of an embedded retaining wall. How do you estimate your lateral earth pressure coefficient for passive conditions? Very similar to the equation I showed for active conditions. The difference here is the plus sign in the middle. And how do you get to this? Again, very similar situation to before, only now your vertical stresses will stay constant, but your sigma prime H will increase, right? Because you have this wall moving into the soil rather than moving away. So let's draw more circles again. Initially, again, your soil, you're assuming, will start at rest, right? So that's highlighted with this blue circle right here, not touching the failure envelope. You have your sigma prime V as your major stress, and then your K naught times your sigma prime V is your minor. As the wall moves, your sigma H will increase, right? So this point right here is going to be moved upward. And as that happens, at first your Mohr circle is going to shrink, right? You'll move this direction until your sigma prime H surpasses your vertical stress, right? You'll move it all the way out here until the circle that you draw actually touches the strength envelope or the failure envelope. So at that point, we have this Kp multiplier times your sigma prime V. That's your passive lateral earth pressure coefficient. Very similar to the active one, but now computed a little bit differently. And we get it in much the same way. So now we're saying, using our Mohr circle drawing over here, we can say sine of V prime is equal to 1/2 sigma prime H minus sigma prime V. Again, that's the diameter, or the diameter of your Mohr circle, over 1/2 of sigma prime V plus sigma prime H. So that's the center of your circle that you're looking at. Rewrite this to solve for sigma prime H, just like before. And again, using some trigonometric relationships, you can rewrite it as tangent squared of 45 plus V over 2 multiplied by your vertical stress. And now we again have this nice multiplier that we can replace with Kp. So your lateral earth pressure coefficient is representing this tangent squared term. And this is how you compute it. Again, very similar to the active condition, but we have a plus instead of a minus. And again, I'm only showing the equations for situations without cohesion, but there are modifications that would include cohesion. So how much movement is required to develop those active or passive conditions? So I mentioned that you have to move the stress high enough or low enough, right, so that you get your Mohr circle to actually touch the failure envelope, right? So that's sort of the assumption here in the Rankine theory, that you're activating your full shear strength. Well, typically your passive pressures are going to be larger and require more movement, right, to fully develop that shear strength compared to your active pressures. You may have noticed that in the past drawings I showed, the Mohr circle for the passive conditions had a much larger diameter of that Mohr circle. So typically the movement ratio, right, so the lateral movement at the top of the wall over the height of the wall needs to be in this range shown in this table for different types of soil. So let's say we're looking at a loose sand. You would need to have relatively little movement to activate your active pressures, your active lateral earth pressures, to get your passive lateral earth pressure fully activated and get your shear strength fully mobilized. You need a little bit more movement. It also varies by different soil type, right? So you would need more movement for clay, in this case, for both active and passive conditions. So what happens if your ground isn't level? All the equations we've shown to this point are assuming level ground. There are a couple of modifications you can make to these lateral earth pressure coefficients, these K values, to account for sloping ground. If we're talking about at-rest conditions, for example, your earth pressure coefficient for slope of beta, all you do is you take your equation for the at-rest condition and multiply it by 1 plus sine beta. And that's how you would adjust your horizontal stress, your lateral earth pressure coefficient for sloping ground. For the active case, it's a little bit more complicated. If you have your back slope here of your fill soil, you would use this equation with a lot of cosines everywhere and betas and phis mixed in there, right? I'm not going to cover the derivation for this because we really don't have much time in this presentation to do that, but I'm sure you could find it if you go looking. But wanted to point out that this is how you would adjust your coefficients for sloping ground. So let's talk a little bit about the assumptions of Rankine theory, some of the limitations, and maybe just some of the practical considerations you need to keep in mind. So far, we've given you the equations for computing your lateral earth pressure coefficients, your Ka, your K naught, and your Kp based on friction angle. So here's some common values based on these two friction angles. And at rest conditions, as I mentioned before, you kind of assume your strength is not fully mobilized, right? Your Mohr circle is not touching the shear strength envelope. And your K naught depends on your soil type and the stress history. So that would incorporate that OCR value. It also incorporates your friction angle. For your active and passive conditions, we assume that your shear strength is fully mobilized, as we mentioned. and that you have no shear stresses on the horizontal or vertical planes for level ground, right? So that's kind of an assumption. And then you have complementary failure planes in backfill at the limit state. So you sort of have these crisscrossing failure planes. In reality, there comes a point where this isn't necessarily true. But these are all sort of the assumptions that we have for Rankine theory. I want to highlight one important note is don't forget, up to this point, we've been using effective stresses to compute our lateral earth pressures in this Rankine theory. So do not compute it with total vertical stresses. Now, I mentioned that's something hopefully you knew before this presentation. You know the difference between effective and vertical stresses. If you do know that difference, you'll understand what I mean when I say use the effective or the prime vertical stress and do not use the total vertical stress, right? So be careful, don't mix them up. Make sure you account for the pore pressures. A few more notes about Rankine theory. Your passive earth pressure coefficient, lateral earth pressure coefficient, will be greater than the at-rest condition, and which will also be greater than the active condition. Your K for the inclined ground condition will be greater than K for your level ground condition. And as your soil density increases, your Ka decreases and your Kp increases. Let me show you where that comes from. So here's a figure showing on the horizontal axis your wall movement over wall height. So that, that ratio of the lateral wall movement over the height. And nope, that's on a square root scale. It's a little bit funky. And on the vertical axis, we have a log scale of your K value, so your lateral earth pressure coefficients. The dashed line is representing a dense sand. And on the left side of the vertical axis here, we're looking at passive movement. On the right side of the vertical axis, we're looking at active movement. So if we follow this dashed line, for example, for a dense sand with a phi prime of maybe 45 degrees, follow that, you'll see it start to dip down as your wall movement over wall height increases, right? Or sorry, decreases. Till you get to this point where you're at rest. Right, so if you're at rest, you can expect a lateral earth pressure coefficient around 0.29 for this dense soil. But if your wall movement into the soil increases, right, you'll get to a higher lateral earth pressure coefficient, somewhere around 5.8. Follow back down here, starting at rest again. If we move in the active condition, right, your wall is moving away from the soil. Here, the dense sand, you'll anticipate a Ka of like 0.17. So 0.17 compared to 0.29, compared to 5.8. You can see how those lateral earth pressures are very different scenarios, right? So as I mentioned, your passive value is going to be greater than at rest and greater than active. And that's the case for both dense sand and loose sand. But if you're comparing the dense to the loose sand, notice that your Kp is less than the Kp of a dense sand. Following the loose sand over here to the active side, your loose sand Ka is greater than your dense sand Ka, right? So keep these two relationships in mind. The difference between the Kp and the Ka is less for this loose sand compared to the dense sand. So I mentioned earlier, you know, we were looking at soils where we're not incorporating cohesion. So we're looking at our granular soils, non-cohesive material. The Rankine theory works pretty well for sands and gravels, not particularly well for cohesive soils. One of the reasons is because clays can dry, they can shrink, crack, swell, soften, and hold water in those cracks. If these cracks develop and water is retained inside of these cracks, they will add additional hydrostatic pressure on the wall than maybe was anticipated. It also means that you're not going to get the same continuity and the same lateral earth pressure developed in this tension crack zone, right? So this really starts to wreak havoc on all of your assumptions for the Rankine theory and will start to cause some issues. So generally speaking, Rankine theory is great for sands and gravels, maybe not a great choice for cohesive soils. There are modified equations, as I mentioned earlier, for all of these lateral earth pressures that include cohesion, but just be careful about how you use them and when you use them. There are other methods to estimating lateral earth pressures. So as I mentioned in this video, I've been focusing on the Rankine method, but there are some others. There's the Coulomb method. This one considers forces instead of stresses. So when we were talking about Rankine, we used our stresses and more circles to come up with the method, or rather Rankine did, but we can see how the method was derived using stresses. In the Coulomb method, we're looking at forces. So you assume failure occurs along a plane, and then you can evaluate the equilibrium of these free body trial wedges. So you draw these wedges on an assumed failure plane and see if you get equilibrium of all your forces. This can take a little bit of extra time, but can be pretty helpful, especially in conditions where you don't feel like Rankine is applicable. It's not a good scenario. You can use it to analyze complex geometries or loads, right? Rankine really works for where you have slope backfill, but if you have really complex geometries or you have non-constant pressures or loads, then Coulomb is a great choice. Coulomb also considers wall friction, but just be cautious about using Coulomb method for passive earth pressures if your wall friction is really high compared to your friction angle of the soil. That's because you start to have really strong mispredictions in the Coulomb method compared to what reality would suggest. Part of that is because in the Coulomb method, we're assuming a linear or a straight flat plane, a failure plane that's straight. But in reality, that plane is probably a little bit curved, especially when you're really close to the wall itself or the object that's moving in or out of the soil. So for passive earth pressures, don't use Coulomb for conditions where your wall friction is really high compared to the V-prop. But that's why there are other methods like the log spiral method, which assumes a curved failure surface, which, as I mentioned, is probably a little bit closer to what is actually happening based on some laboratory tests that have been done in the past. In this method, it's a little bit more complicated. So it's a graphical method you can apply. There are some charts or tables that help you apply this method. There are also computer programs that can help with that. So a little more complicated, but useful in scenarios where Coulomb or where Rankine are not great choices. It's also useful when you're computing passive earth pressures outside of the applicable range for Coulomb, like I just mentioned. But one of the reasons why Rankine is still a common one to teach and have in your toolbox is because it's simple and often can be pretty conservative. So when you can use it, it's a great option. But in scenarios where you think that you'll be too conservative and end up with too much cost to build what you're building, maybe you'll choose one of the other methods to back it up. So let's talk a little bit about lateral earth pressure analyses in what we're calling the real world. So everything on paper so far looks pretty straightforward and hopefully clear. But let's talk about some other realities and considerations to keep in mind. Drainage is important, for one thing. If you have water collecting behind the wall or running over the top of the wall, that can cause some problems. So you'll get erosion in the backfill soil, increased hydrostatic pressure on the wall, things like that. As you can see in this particular illustration, you can have water seeping through the wall. Maybe you've seen that before on a wall that wasn't designed to accommodate the runoff that it's experiencing. And here you can see all this water accumulating back here in the backfill. And here it says that you're getting water pushing the wall away, right? Because you're not having sufficient drainage here. So the ideal scenario is where you have some drainage options. There's a perforated drain pipe that goes through the wall to allow water to go out the front. You also have sort of these pipes along the wall that allow the water to flow away from the block, right? And you'll also make sure you have some well-draining soil material here too, so that you're not retaining a lot of water where you don't want it to be. All right. Keep in mind drainage. Another interesting thing is that mechanically stabilized earth walls are pretty common, and you've probably seen a lot of these out on your drives near freeways, overpasses, and things like that. So some types of retaining walls aren't really designed to fully retain the soil, as we've been talking about, but rather engineers can reinforce the soil so that the soil essentially holds itself up and the wall is there for erosion control and for aesthetics, right? So these panels that you're seeing right here essentially are just covering for the mechanically stabilized earth walls, which is basically this section here where you have soil layered in between these soil reinforcements, right? Which are these sort of dashed lines. So you have grids that help reinforce the soil, different kinds of materials that you can just layer in between layers of soil, like a really, really tall cake. And the soil is able to hold itself up in that condition. And so this wall here is really just a facing, not holding up the wall or not holding up the soil itself, because the soil is able to hold itself up. Let me just wrap up with a few notes. So we've really only barely scratched the surface of lateral earth pressures, and there's probably a lot more to it that I don't know and haven't learned yet. It does get more complicated than what I've just presented when the backfill soil is clay, not sand. So we talked about equations where we're not incorporating cohesion and where we're talking about well-draining material. It's a little more complicated when the backfill is layered with different types of soil. So the example I provided showed one type of soil all the way down the entire height of the wall. But what happens if you have a little bit different types of soil? You can use the Rankine theory to make that work, but it just gets a little more complicated. What about the situation where you want to account for friction between your soil and a wall? I mentioned that in the Coulomb method, but we really didn't go into detail about how do you do that. And also, maybe you want to consider additional temporary loading from earthquakes or some other horizontal shaking, right? Also, how would you account for other temporary point loads or strip loads and other things up behind the wall? There's a lot more to it. And then how do you actually design the wall in the first place? So if you're interested and you'd like to learn more about retaining walls and foundations, I highly recommend taking a graduate level foundations class and learning more about it. So thank you very much for your time, and I hope you have a great day.